Hello! Today, we're going to dive into the world of logarithmic functions. These are powerful tools we can use to model all sorts of real-world phenomena. Our main objective is to learn how to construct a logarithmic function model from given data or scenarios. You'll see that logarithmic models are incredibly useful in fields like science, economics, and even just understanding everyday processes. So, what exactly is a logarithmic function? The most important thing to understand is that it's the inverse of an exponential function. You're probably familiar with exponential functions like y equals b to the power of x, where b is the base. This describes repeated multiplication. An exponential function asks, we start with a value and multiply it by a certain factor, b, a certain number of times x. What is the final value, y? Now, a logarithmic function flips this question around. Its standard form is x equals log base b of y. It asks the question, how many times must you multiply the base, b, by itself to get a final value of y? Let's translate that more directly. The statement log base b of y equals x is equivalent to saying b to the power of x equals y. They are just two different ways of stating the same mathematical fact. One is asking what is the exponent, and the other is performing the exponentiation. Think of it this way. Log base b of y equals x answers the question, to what power must I raise b to get y? The answer is x. This inverse relationship is the core idea behind logarithms. So, with that definition in mind, when would we want to use a logarithmic model instead of a linear or exponential one? The key is how the rate of change behaves. Exponential models show constant proportional change. Think of doubling your money. The growth from $100 to $200 is $100. But the growth from $10,000 to $20,000 is $10,000. The change is proportional, but the absolute amount increases as the input grows. Logarithmic models show constant proportional change in reverse. This means the rate of change decreases as the input increases. They have a fast start and then slow down, or flatten out. Let's visualize this. Imagine the graph of a simple exponential function. It starts low and increases steeply, getting steeper and steeper. This represents accelerating growth. Now look at a simple logarithmic function. It starts steep, but then flattens out. The first few changes in input create large changes in output. But as the input gets large, you need a much larger change in input to get the same change in output. The rate of change is decreasing. This pattern of diminishing returns is the hallmark of a logarithmic model. We'll use this visual cue to decide if a logarithmic model is appropriate for a dataset. So, where do we see this diminishing returns pattern in the real world? All over the place. Classic examples are logarithmic scales like the Richter scale for earthquakes, the pH scale for acidity, and the decibel scale for sound. These scales compress a huge range of energy or intensity into a much smaller, more manageable range of numbers. Other examples include population saturation, where initial growth is rapid but then slows as resources become scarce, and learning curves, where you learn a lot very quickly at first, but the rate of improvement slows over time. Let's make the inverse relationship concrete with a simple example. Suppose we have a bacteria population that doubles every month. This is exponential growth. After times, starting with 100 bacteria, the population P is given by P of T equals 100 times 2 to the power of T. After 4 months, the population is 1600. Now, let's look at the inverse. A logarithmic model. Imagine a stimulus that doubles in intensity, and each doubling gives us a +1 response. The response R is R of x equals log base 2 of x, where x is the stimulus. To get a response of 4, you need a stimulus of 16. Here's the key insight. When the output of a logarithmic function is a whole number, it tells you exactly how many times the base was multiplied by itself. For example, the equation log base 2 of 32 equals 5 means that you must multiply 2 by itself 5 times to get 32. Let's check that. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. It works. The logarithm tells us the number of multiplications. Okay, let's move on to our main objective, constructing these logarithmic models. We'll explore a few methods. Our first method is for when we know the base or proportion, and a 0 point, which is a point where the function's output is 0. The general form of the model is L of d equals a times log base b of the quantity d minus h, plus k. He is a horizontal shift, and k is a vertical shift. The 0 point helps us find h and k. Let's work through an example. Sound intensity decreases logarithmically. At a distance of 10 meters, the loudness is 20 decibels. At 100 meters, it's 0 decibels. We can assume the horizontal shift, HA, is 0, since it's logical that at a distance of 1, the loudness would be high. We also know the base is 10. So our model becomes L of D equals A times log base 10 of D plus K. We need to solve for A and K using our 2 points. Let's substitute the first point. 10 meters gives 20 decibels. We know that log base 10 of 10 is 1. Why? Because 10 to the first power is 10. So our equation simplifies to 20 equals A plus K. Now let's substitute our second point. 100 meters gives 0 decibels. Log base 10 of 100 is 2, because 10 squared is 100. This gives us 0 equals 2A plus K. Now we have a system of two linear equations with two variables. The easiest way to solve this is by subtracting the second equation from the first. 20 minus 0 is 20. A minus 2A is negative A. And K minus K is 0. So 20 equals negative A, which means A equals negative 20. Now that we have A, we can find K. We know A plus K is 20, so negative 20 plus K is 20, which means K must be 40. Our final model is L of D equals negative 20 times log base 10 of D, plus 40. This model correctly captures that loudness decreases as distance increases. The previous method worked well because we knew the base was 10. But what if we don't know the base, and we don't have a 0 point? Method 2 is a more general approach for when you are given just 2 data points. When we have two input-output pairs, we typically use the general form, f of x equals a plus b times the natural log of x. The natural log, written as ln, is the logarithm with a base of e, which is an irrational number approximately equal to 2.718. You'll see why we use this special base later, but it's very common in modeling. Let's consider an example of website traffic. The model is for the number of visitors, v, as a function of the number of months, m. We have 2 data points. After 1 month, there are 500 visitors, and after 10 months, there are 800 visitors. This looks like a logarithmic pattern. The traffic increased a lot in the first month, but then slowed down, only adding 300 visitors over the next 9 months. Let's build a model. First, we substitute the point, 1/500, into our model. Here's a crucial fact. The natural log of 1 is always 0. This is because e to the power of 0 is 1. So the equation simplifies to 500 equals a. We found one variable. Now we substitute the point, 10/800, into the model. Since we now know that a is 500, we write 800 equals 500 plus b times ln of 10. We can subtract 500 from both sides, which gives us 300 equals b times ln of 10. To solve for b, we divide by ln, 10. Using a calculator, ln of 10 is approximately 2.3026. So b is about 130.29. Putting it all together, our logarithmic model for website traffic is v of m equals 500 plus 130.3 times the natural log of m. This model now allows us to predict traffic at any point in time. A third way to think about constructing models is through transformations of the parent function. Our parent logarithmic function is just y equals log base b of x. Its graph is a simple curve passing through 1, 0. By applying transformations, we can create more complex models. The general transformed form is f of x equals a times log base b of the quantity x minus h plus k. Each of these constants has a specific effect. The constant a causes a vertical stretch or compression. If a is negative, it also flips the graph over the x-axis, which is called a vertical reflection. The constant h causes a horizontal shift. Adding h moves the graph to the left, and subtracting h moves it to the right. Finally, k causes a vertical shift. Adding k moves it up, and subtracting k moves it down. Let's see these in action with two important scientific examples. First, the pH scale. The formula is pH equals negative log base 10 of the hydrogen ion concentration. This model has a B of 10, the base of our number system. It also has an A of negative 1, which means the graph is reflected vertically. The more hydrogen ions you have, the more acidic the solution, and the lower the pH number. The reflection makes this inverse relationship work. Second, let's look at delayed growth. Imagine a plant doesn't start growing until a certain time, say 5 months. A model for its height, h of t, could be 3 times log base 2 of the quantity t minus 5 plus 10. Here, the h of 5 causes a horizontal shift to the right. The growth curve starts at t equals sine 5. The k of 10 is a vertical shift up, meaning the initial height at t equals sine 5 is 10 units. The b of 2 and a of 3 define the rate and amount of logarithmic growth after the delay. By transforming the parent function, we can capture complex real-world situations like this. What if you have a lot of data points, not just 2, and you're not sure how they're related? This is where technology becomes incredibly useful. We can use logarithmic regression on a graphing calculator. The process is straightforward. First, you'll enter your data, press the Stat button, then select Edit. You'll enter your input data into list 1, L1, and your output data into list 2, L2. Once your data is entered, you'll perform the regression, go back to the Stat menu, arrow over to Calc, and then select LNREG, which stands for logarithmic regression. On most calculators, this is option 9. The calculator will then give you an equation in the form y equals a plus b times ln of x. It will also give you an r² value, or coefficient of determination. This number, between 0 and 1, tells you how well the model fits your data. A value closer to 1, like 0.96 in our example, means it's a very good fit. Let's apply this. Here's a table of hours studied versus test score. A student studies for 1 hour and gets a 55, then 2 hours for a 68, and so on. Notice the pattern? The score improvement for the first hour is 13 points, but for the last 4 hours it's only 7 points. This is diminishing returns, a perfect candidate for logarithmic regression. If you plug this data into your calculator and run a logarithmic regression, you'll get the model y equals 43.2 plus 15.8 times ln of x. The r² value is 0.96, which is excellent. It means this model explains 96% of the variation in the test scores. This technology is incredibly powerful for analyzing real-world data and finding the best fit. A very special and important type of logarithmic model is one that uses the natural logarithm, or ln(x). As we briefly mentioned, the natural logarithm is just a logarithm with a base of e. E is a special irrational number, like pi, that shows up everywhere in nature and mathematics. It's approximately 2.718. So why is this base so special? It's often called the base of continuous growth. It's the natural base for describing continuous processes. For instance, in calculus, the derivative of the natural log is incredibly simple. This makes it a foundational tool in higher-level math and science. Because of this, it appears in many important formulas in physics, biology, and finance. Let's look at 3 classic applications that use the natural log. First, compound interest that is compounded continuously. The formula is a equals p times e to the power of r times t. If you want to solve for the time t takes to reach a certain amount, you'd use the natural log. After a few steps of algebra, you'd find that t equals the natural log of the ratio a over p, all divided by r. Second, the half-life formula for radioactive decay. The time it takes for half of a substance to decay is given by T1/2 equals ln of 2 divided by the decay constant k. This is a logarithmic relationship that connects the decay rate to the time it takes to lose half its mass. Third, Newton's law of cooling, which describes how the temperature of an object changes over time as it approaches the ambient temperature. If you want to find the time it takes to reach a certain temperature, you'd solve this equation using the natural log. The natural log is not just a mathematical curiosity, it's a fundamental tool for describing the continuous change we see all around us. Let's work through a full example using the half-life concept. The problem states that carbon-14 has a half-life of 5,730 years. Our goal is to figure out the age of an ancient artifact if it has only 40% of its original carbon-14 remaining. We'll use the half-life formula. The amount remaining, n, equals the initial amount, n0, times e to the power of negative kt. Here, k is the decay constant, and t is the time. Step 1 is to find the decay constant k. We can use the half-life for this. The definition of half-life is the time it takes for half of the substance to be left. So, after 5,730 years, the remaining amount is half of the starting amount. We can write this as 0.5 times n0. The n naughts cancel out, leaving us with 0.5 equals e to the power of negative 5,730k. To solve for k, we need to get it out of the exponent. We do this by taking the natural log of both sides. This gives us k equals the natural log of 0.5 divided by negative 5,730. Using a calculator, we find that k is approximately 0.000121. Now for step 2, use k to find the age of the artifact. We know 40% is remaining, so n equals 0.4 times n naught. We substitute this, along with our new value of k, into the formula. Again, the n naughts cancel. We take the natural log of both sides, giving us natural log of 0.4 equals negative 0.000121 times t. Solving for t, we get natural log of 0.4 divided by negative 0.0000121. The result is approximately 7,578 years. So, our logarithmic model tells us the artifact is about 7,500 years old. That's a powerful application. Once you have a model, one of its main purposes is to make predictions. Logarithmic models can be used in two primary ways for this. Let's use our website traffic model from earlier. The number of visitors, T of m, equals 200 plus 85 times the natural log of the months, m. The first type of prediction is direct prediction. This is when you are given an input and you find the output. For example, what will the traffic be at month 24? You simply substitute 24 for m into the equation. T of 24 equals 200 plus 85 times the natural log of 24. A calculator gives us an answer of about 470 visitors. This is a direct calculation. The second type is inverse prediction. This is when you are given an output and you need to find the input. For example, when will the traffic reach 500 visitors? Here, we set T of m equal to 500 and solve for m. Subtracting 200 gives us 300 equals 85 ln of m. Dividing by 85 gives us ln of m equals 3.529. To solve for m, we exponentiate with base e on both sides. M equals e to the power of 3.529, which is about 34.1 months. This requires using the inverse relationship of logarithms to solve. A very important caution when making predictions is to distinguish between interpolation and extrapolation. Interpolation is predicting within the range of your original data points. This is generally reliable because you're using the model in a domain where it's been shown to fit the real-world behavior. Extrapolation, on the other hand, is predicting beyond that range. You need to use caution here because you are assuming that the trend you've observed in your limited dataset will continue forever. Real-world situations often have constraints. Let's look at an example caution. A model for learning, S of h, might predict skill level based on hours practiced, h. A model like S of h equals 30 plus 20 ln of h fits learning data well for a while. It shows that initial hours of practice have a big impact, but after many hours the improvement is much smaller. This fits reality. However, let's extrapolate. According to this model, after 100 hours of practice, a student's skill level would be 122. The model predicts unlimited growth in skill. Is that realistic? No. Eventually, everyone hits a plateau and can't get any better. So, when you extrapolate, you must ask yourself, is a logarithmic model still appropriate for this far-out prediction? Or is there a real-world limit that the model doesn't account for? Always check your assumptions before making confident predictions outside your data range. Let's summarize everything we've learned with a quick self-check. Take a moment to think about the answer to each question before I reveal it. Question 1. What does the statement log base 3 of 81 equals 4 mean in words? The answer is, you must raise 3 to the power of 4 to get 81, or equivalently, 3 multiplied by itself 4 times equals 81. Question 2. True or false? Logarithmic models show an increasing rate of change. The answer is false. Logarithmic models show a decreasing rate of change, or diminishing returns. They are steep at the beginning and then flatten out. Question 3. Why do we use the natural logarithm in models involving continuous growth? The answer is because its base, a, is the natural base for continuous processes. It simplifies the math and calculus and appears in many scientific and financial formulas. It truly is the natural choice for continuous change. Let's recap what we've accomplished today. You can now construct a logarithmic function model to describe situations with diminishing returns. We started by defining logarithms as the inverse of exponential functions, learning how to translate between the two forms. We explored how logarithmic models capture diminishing returns, a pattern of change that is fast at the start and then slows down. We learned two primary methods for constructing models, one from a base and a 0 point, and another from two general data points. We also saw how transformations can be used to shift and shape logarithmic graphs to fit different scenarios. Finally, we explored how to use technology to perform logarithmic regression on larger datasets, and we learned to use caution with extrapolation, understanding that models are best used within the range of the data that created them. The key takeaway is that logarithmic models are essential for capturing situations of diminishing returns. Understanding this pattern will help you analyze data and make sense of many real-world phenomena. Thank you for watching. Keep practicing and exploring these powerful functions.